Picture this. A critical software system crashes unexpectedly. The consequences? Lost data, disrupted operations, and frustrated users. Recovery testing steps in as the unsung hero, ensuring that systems can gracefully recover from such failures. It's about more than just fixing bugs. It's about building resilience into the very core of the software. Recovery testing focuses on how well a system bounces back from failures, be it a system crash, hardware malfunction, or network outage. It's a critical aspect of software quality assurance, often overlooked but absolutely essential in today's world of complex and interconnected systems. This type of testing goes beyond simply identifying defects. It helps us understand the system's ability to withstand and recover from unexpected events. By simulating real-world failure scenarios, we gain valuable insights into the robustness and reliability of the software. In essence, recovery testing is about asking the tough questions. What happens when things go wrong? How quickly can the system recover? Is data integrity maintained? These are the questions that keep project managers and software testers up at night, and rightfully so. In the realm of software development, quality reigns supreme. Users demand software that is not only functional, but also reliable and resilient. Recovery testing plays a pivotal role in achieving this goal. By incorporating recovery testing into the SQA process, we proactively address potential points of failure. This leads to more robust and dependable software that can withstand the test of time. Moreover, recovery testing provides valuable insights into the system's architecture and design. By observing how the system behaves under stress, we can identify weaknesses and areas for improvement. Ultimately, investing in recovery testing translates into a host of benefits: reduced downtime, minimized data loss, improved customer satisfaction, and enhanced brand reputation. It's an investment that pays dividends in the long run. The world of software is fraught with potential pitfalls. Systems crash, hardware fails, and networks go down. Recovery testing helps us prepare for these eventualities by simulating a wide range of failure scenarios. One common scenario involves simulating a system crash. This could be due to a software bug, a power outage, or any other event that brings the system to a halt. Recovery testing in this case would involve verifying that the system can restart gracefully and resume operations without data loss. Another scenario focuses on data recovery. What happens if the database server crashes or a storage device fails? Recovery testing ensures that critical data can be restored from backups and that data integrity is maintained. Network failures are also a common occurrence. Recovery testing can simulate scenarios like network outages or connectivity issues to assess the system's ability to reconnect and resume operations seamlessly. By testing these and other real-world scenarios, we gain confidence in the system's ability to handle unexpected events and recover gracefully. Recovery testing encompasses a variety of techniques, each designed to test different aspects of system resilience. Let's delve into some of the most common types: restart testing, data recovery testing, and failover testing. Restart testing, as the name suggests, focuses on the system's ability to restart after a failure. This involves abruptly shutting down the system and then restarting it to verify that it comes back online properly. Data recovery testing examines the system's ability to recover data after a failure. This could involve restoring data from backups, verifying data integrity, or testing data replication mechanisms. Failover testing is crucial for systems that require high availability. It involves simulating the failure of a primary system component and verifying that the backup or secondary component takes over seamlessly. Each of these testing types plays a vital role in ensuring the overall resilience of the software. By employing a combination of these techniques, we can build systems that are robust, reliable, and capable of handling unexpected events. Section 5. Restart testing. Ensuring system resilience. Imagine a web server suddenly crashing during peak hours. Restart testing ensures that such a crash doesn't translate into a prolonged outage. This type of testing focuses on the system's ability to recover from unexpected shutdowns or failures. The process typically involves forcing the system to shut down abruptly, simulating a power outage or system crash. Testers then observe how long it takes for the system to restart and resume normal operations. Key metrics to monitor during restart testing include the time it takes for the system to reboot, any error messages encountered during the process, and the system's overall stability after restarting. Effective restart testing helps identify bottlenecks in the system's startup process and ensures that critical services are restored promptly, minimizing downtime and user disruption. Section 6. Data recovery testing, safeguarding information integrity. Data is the lifeblood of many software systems. Data recovery testing focuses on the crucial aspect of safeguarding this valuable asset in the event of a failure. This type of testing simulates scenarios where data might be lost or corrupted, such as database crashes, storage device failures, or accidental data deletion. The goal is to verify that data can be restored to a consistent and usable state. Testing typically involves restoring data from backups, verifying data integrity using checksums or other validation techniques, and testing data replication mechanisms to ensure data redundancy. By rigorously testing data recovery procedures, organizations can minimize the risk of data loss, ensure business continuity, and maintain the trust of their users. Section 7. Failover testing, achieving high availability. In today's always-on world, high availability is paramount for mission-critical systems. Failover testing plays a crucial role in ensuring that systems remain operational even when components fail. This type of testing focuses on simulating the failure of various system components, such as servers, databases, or network connections. The goal is to verify that the system can seamlessly switch over to redundant or backup components without interrupting service. Testers typically use techniques like network disconnections, server shutdowns, or database crashes to trigger failover mechanisms. They then monitor the system's behavior, measuring failover time, data consistency, and overall system performance during the failover process. Effective failover testing helps identify any weaknesses in the system's redundancy mechanisms and ensures that critical services remain available even in the face of component failures. Section 8. Best practices for effective recovery testing. Recovery testing, while essential, can be complex and challenging. Here are some best practices to ensure its effectiveness. 1. Start early and test often. Integrate recovery testing into the software development lifecycle from the outset. Regular testing helps identify and address issues early on. 2. Prioritize real-world scenarios. Focus on simulating realistic failure scenarios that are relevant to the system's operating environment. 3. Automate where possible. Automate recovery testing procedures to improve efficiency and consistency, especially for repetitive tests. 4. Monitor and analyze results. Carefully monitor test results, analyze system behavior, and document findings to identify areas for improvement. 5. Collaborate and communicate. Foster collaboration between developers, testers, and operations teams to ensure a holistic approach to recovery testing. Section 9. The future of recovery testing. As software systems become increasingly complex and interconnected, the importance of recovery testing will only continue to grow. The future of recovery testing lies in embracing new technologies and methodologies to enhance its effectiveness. Cloud computing, with its distributed nature and reliance on virtualization, presents unique challenges and opportunities for recovery testing. Testers need to adapt their strategies to account for the dynamic and ephemeral nature of cloud environments. Artificial intelligence and machine learning are also poised to play a significant role in the future of recovery testing. AI-powered tools can help automate test case generation, analyze vast amounts of data to identify potential failure patterns, and even predict system behavior under stress. The rise of microservices-based architectures, where applications are composed of small, independent services, also demands new approaches to recovery testing. Testing needs to focus on the resilience of individual services and their ability to recover independently without impacting the overall system. Section 10. Conclusion: Recovery testing, a cornerstone of reliable software. In today's technology-driven world, software failures can have far-reaching consequences. Recovery testing stands as a critical line of defense, ensuring that systems can withstand unexpected events and recover gracefully. By embracing a comprehensive approach to recovery testing, organizations can build robust and resilient software that meets the demands of today's users. From simulating system crashes to testing data recovery procedures, each aspect of recovery testing plays a vital role in ensuring system reliability. As software continues to evolve and become more complex, the importance of recovery testing will only continue to grow. By embracing best practices, incorporating new technologies, and fostering a culture of resilience, we can build software that stands the test of time.